Good morning. So the title of my presentation is Performance Analysis of FSO System over Generalized Turbulence Channel with Pointing Errors using PLSK Signaling Technique. So myself is Vinith Pandiyembu and my co-authors are K. Prabhu, Jagdish V.K., P. Muthuchidambaranathan and Sunday Ekpo. Introduction. The demand for high data rate transmission is increasing because of high data intensive applications and huge increase in the number of users. So due to these reasons, the existing RF technology is not capable of meeting all these demands. So now in order to meet this demand, we can use optical wireless or free space optical communication systems. Free space optical communication or simply FSOC systems use optical signals to transfer information between users via line of sight wireless communication techniques. So it has many advantages compared to the RF systems, like it uses the license-free spectrum, it has high data rate, it has good link security, it is easy for deployment and reconfiguration, and it is very cost effective. The objectives of the presentation are firstly to study the performance of FSOC links over the generalized atmospheric turbulence channel, to study the effect of fading faced by these optical signals due to the atmospheric turbulence, to study the effect of the pointing error fading on these optical signals, and to derive the bit error rate and channel capacity performance of the PLSK based FSOC system. System model. The considered FSOC system consists of a PLSK based optical transmitter, and it is transmitted, the signals are transmitted over the M distributed channel, and the receiver is also fitted with a PLSK demodulator. PLSK modulation is nothing but polarization shift key. So here the data is modulated using the different polarization of the optical signals. Now at the receiver, the detected signal Y can be expressed as Y is equal to R into H into X plus M. So here X is the signal transmitted, R is the responsivity of the receiver aperture, and H is the atmospheric fading channel coefficient. And actually H consists of three terms. H is equal to HL into HA into HP, where HL is the attenuation due to the path loss, which is deterministic in nature, whereas HA and HP are random in nature, and they have the fading coefficients due to the channel turbulence as well as the pointing errors respectively. And also an additive white Gaussian noise also gets added to the received signal. Channel model. The transmitted optical beam is affected by the channel turbulence as well as the pointing errors. Channel turbulence is due to the difference in the refractive index along the path of the optical signal due to the varying pressures and temperature in the atmosphere. And the pointing error is due to the misalignment between the transmitted and received optical beams. So these two fading phenomena are in fact random in nature, and they are also independent of each other. So they can be combinedly modeled using the PDF of the Malaga distribution, and it can be given as FH of H is equal to G square A by 2 into H raised to minus 1 into sigma of K equal to 1 to beta AK into alpha beta divided by mu beta plus omega dash the whole raised to minus alpha plus K by 2 into major G function G of 3, 0, 1, 3 alpha beta into H divided by mu beta plus omega dash into A naught, and parameters G square plus 1 at the top and G square comma alpha comma K at the bottom, wherein A and AK are given by the below given expressions. Now let us see the performance analysis. Firstly, we will do the bit error rate, BER. So to compute the BER, we need the SNR. SNR is nothing but the ratio between the signal power and the noise power of the receiver. And SNR of this PLSK based FSOC system will be equal to SNR of H is equal to R square into H into PR divided by 2 sigma n square, where PR is the received signal power and sigma n square is the noise power variance. Now the BER for this system can be expressed as PEC of H is equal to 0.5 into exponential function of minus R square into H into PR divided by 4 sigma n square. But this BR is actually time varying in nature. Since the BR expression we have seen is time varying in nature, so it is better to calculate the average BR. Now it can be computed by finding the average BR or else ABR by integrating the instantaneous BR over the channel PDF. So now if we substitute for this channel PDF as well as the conditional time varying BER, and if we integrate this resulting integral using the identity for this integration of these major G functions, we can get the final closed form expression for the BER as given as P is equal to G square into A into B raised to alpha by 2 divided by 4 into root pi into sigma of k equal to 1 to beta AK into 2 raised to k into B into major G function G 2, 3, 4, 3 R square PR into A naught into B divided by 2 sigma n square with parameters 1 minus G square, 1 minus alpha, 1 minus k, 1 at the top and 0, 1 by 2, minus G square at bottom. So here the term B is equal to mu into beta plus omega dash divided by alpha into beta. For getting better insights into this BR expression, we can find the asymptotic BR expression by expressing the BR in terms of very high SNR. So then the major G functions can be approximated in terms of the gamma functions. So now also we can express the BR function in terms of the SNR as well as the diversity gain and coding gain. So therefore alternately we can write P approximately equal to GC into zeta down raised to minus GD, where GD is the diversity gain and GC is the coding gain. And now comparing this expression with the asymptotic BR expression given at the top, we can see that the coding gain GC is equal to G bar all raised to minus 1 divided by K1, m, where G bar is given by this expression and the diversity gain GD is equal to minus K1, m, which is equal to the minimum of G square, alpha, K. The next performance parameter is the channel capacity. So according to Shannon theorem, the maximum achievable channel capacity of the proposed system can be expressed as C of H is equal to log to the base 2 of 1 plus R square H into PR divided by 2 sigma n square. So since again this is in time varying in nature, therefore we can find the mean value of this by integrating it over the channel period. So therefore equivalently we can express this CERG in this integral form. Now the CERG integral can be simplified by expressing the log function in terms of the major G function as given by the expression given at the top. Now this integral can be easily solved using the identity given in this reference, and so we can get the final closed form expression for the channel capacity, which is equal to C, which is equal to G square into A B raised to alpha by 2 divided by 2 ln of 2 into sigma k equal to 1 to beta AK into B raised to k by 2 into major G function 1, 5, 2 of R square PR into B into A naught divided by 2 sigma n square with top parameter K2 and bottom parameter 1 minus 1, minus G square, 0, wherein K2 is equal to 1, 1, minus G square, 1 minus alpha, 1 minus K. The obtained expressions for the channel capacity as well as the BER can be expressed using the plots. So firstly, here the average BER is plotted against average SNR for different values of channel turbulence. So for rho equal to 0 we have high turbulence, and for rho equal to 1 we have low turbulence. Here we have plotted both the asymptotic as well as non-asymptotic curves. So the blue curves correspond to the non-asymptotic curves and the red lines correspond to the asymptotic curve. So here we can see that at the top we have rho equal to 0 curve, and at the bottom we have rho equal to 1 curve. So which show that as the value of the channel turbulence reduces, raw value reduces, and we have better average BER. Here again the BER is plotted for varying pointing error values. So the pointing error parameter is represented by G. So as G increases, the effect of the pointing error reduces. So here we have plotted for two different G values, G equal to 5.03 and G equal to 1.68. So you can see that as the value of G increases, the pointing error reduces, and we have better BER performance. So here both the non-asymptotic as well as asymptotic curves are also plotted. So also we can verify that as the SNR increases, the asymptotic curves overlaps with the non-asymptotic curves. In this plot, the ergodic channel capacity is plotted against the average SNR. So here we have plotted for the varying values of rho as well as G, that is for varying channel turbulence as well as varying values of pointing error. So once again you can see that the red lines or red curves correspond to the high pointing error case, and the blue curves correspond to the low pointing error case. So therefore once again we can verify that as the pointing error increases, the channel capacity reduces. Now coming to the conclusion, we can tell that the FSO communication technology is a new communication technology which is using optical signals for wireless data transmission, and it has many advantages such as easy installation, cost effectiveness, license fee spectrum, and high data rate. So here for a POLSK based FSO system, the average BER as well as the channel capacity expressions are derived and plotted, and our results suggest that the single hop FSO system performance is drastically affected by the fading due to the channel turbulence as well as pointing errors. So we need other techniques like channel coding or diversity techniques, etc., to improve the performance. These are the references. Here are the second set of references. Thank you.